Hi everyone, welcome to today's video. Today we are going to solve some problems in magnetically coupled circuit. So let's start with the first question. Here is the first question. For the three coupled coils in the figure, calculate the total inductance. Okay, we have to calculate the equivalent inductance of this network, and we know if two coils are connected in series, we know the equivalent inductance if dot on marked on entering side of both coils L1 plus L2 plus 2M, and if one on the entering side and the other on the leaving side, L1 plus L2 minus 2M. With this concept we are going to solve this problem. We can solve this problem in so many ways with for our convenience. So let me do with the first method. And we know in series connection the inductance are added up. So we can say 6 plus 8 plus 10 is the total inductance, plus here look, the current is entering on one side and leaving on the other side. So between these two inductance the mutual flux is opposing in nature. So minus 8 2M, I am taking the double of this value, minus 8. Between these two, here it is leaving, here it is entering. So minus 10, and here entering. So plus 4, which is equal to 16, 24 minus 18 minus 14, that is equal to 10 Henry. Okay, we can solve in another way, that is method 2. We will get same answer in every cases. Let us consider these two coils. Consider the first coil 6 Henry, and with this coil the 6 Henry, that is the mutual inductance is opposing in nature. So minus 4, and here it is entering plus 2. Okay, and take the other one 8 plus take entering leaving minus 4, here leaving entering minus 5. Okay, take the other one 10 plus entering leaving minus 5 entering plus 2, and what will we get? 6 minus 4 2 plus 2 4 plus 8 12 minus 4 8 minus 5 3 13, 8 plus 2 equal to 10 Henry. Okay, so in every method we will get the same answer. We can follow whatever method is convenient to us. Okay, so let's go to the next problem. The second problem is determine the L equivalent between terminals A and B. So its answer will be 8 plus 9 plus 10 plus here entering 4, 2 into 2 is 4, here it is entering, here it is leaving 3, minus 3 into 2 is 6. Here entering, leaving. So minus 8, and the answer would be 17 Henry. Okay, right? Let's go to next question. Let's start with the third question. Calculate the phasor currents I1 and I2 in the circuit shown below. Here is the circuit for you, and apply KVL in the first loop. We get plus minus. Okay, 12 minus, fall in potential. Due to this minus sign we are replacing, J4 into I1, fall in potential, minus J5 into I1, and due to this mutual flux, here current is entering through this loop and leaving through this loop. So it is opposing in nature, which means falling potential is replaced by plus J3 into I2, which is equal to 0. That is 12 plus J3 I2 minus J1 I1, which is equal to 0, or 12 is equal to Ji1 minus J3 I2. Let this be equation number 1, and apply KVL in second loop. We get minus plus minus, minus J6 into I2 minus 12 I2, opposing nature, so plus J3 into I1, which is equal to 0, or we can say J3 I1 is equal to I2 into 12 plus J6, or I1 is equal to I2 into 12 plus J6 divided by J3, which is equal to what? I2 into 2 minus 4J. I1 is equal to I2 into 2 minus 4J. Let this be equation number 2. And solving these two equations, we will get the value of I1 and I2 here. Substitute the value of I1 in equation number 1. So we will get 12 is equal to J into, what is I1? I2 into 2 minus 4J minus J3 I2. 12 is equal to I2 into 2J plus 4 minus J3, which is equal to I2 into 4 minus J, or 12 is equal, I2 is equal to 12 divided by 4 minus J, and we get the value of I2 as 2.91 angle 14.04. Do in calculator and we will get the value like this. Okay, and substituting the value of I2 in this equation we will get I1 is equal to 13.01 angle minus 49.39 amperes. Okay. Well, let's start with the next question. Determine the value of K. K is nothing but coefficient of coupling for series resonant in the network shown below. Okay. We know for series resonance, at resonance condition, omega equal to omega naught, where XL equivalent is equal to XC equivalent. That is, the reactance offered by the equivalent inductance equal to reactance offered by the capacitors, equivalent capacitor. Okay, here the XC equivalent is equal to 12, which is given in the question. Okay, so what will be XL equivalent? XL equivalent is nothing but 12. Okay, this is our equation number 1. Now, what is XL equivalent? These two inductance are connected in series and current is entering through this dot terminal and leaving through this dot terminal. Okay, therefore, L equivalent is equal to L1 plus L2 minus 2M. And we know what is M? M is nothing but K into root L1 L2. So, replace M with this value. What is L1? J8 plus J8 minus 2 into K into root J8 into J8. Okay. And we know XL equivalent is nothing but J omega L, and here we have to multiply this whole term with omega, then it becomes J omega L equivalent, which is nothing but our what? Reactance. So we can write 12 is equal to, here omega and omega get cancelled, J and J get cancelled. The end, at the end we get 12 is equal to 8 plus 8 minus 2K into 8, that is 16. Minus 4 equal to minus 2K into 8 to 4, which implies K equal to 1 by 4. In the question they are asked for the value of coefficient of coupling K is equal to 1 by 4. Okay. Let's see the next question. Determine output voltage V0. Look at the figure in which we have given V of t, number of turn, the turns ratio is 1:n, and V0 is nothing but the voltage across the load impedance. Okay, now let us consider the input voltage polarity be like this, and the dot is marked over here, so this is nothing but plus minus because the current is flowing in this direction. So this is nothing but plus minus, and this is equal to V2. And we know in transformer V1 by V2 is equal to N1 by N2, and here it is given that 1 by n. So V2 is equal to n into V1, which is equal to n into, what is V1? Vi sin omega t. Okay, and here V2 is equal to here plus minus, and we notice nothing but the opposite polarity of V2, which means V2 is equal to minus V0, or we can say V0 is equal to minus n into Vi into sin omega t. Okay, this is nothing but the output voltage V0 across the load impedance. Okay, in question number 6, we have to calculate the value for n for maximum power transfer in the network shown in the figure. N is nothing but number of turns in the primary, and P is nothing but maximum power transfer theorem. Let me recall two things first. In maximum power transfer theorem, in order to transfer maximum power to the load, the source resistance should be equal to load resistance. Okay, the other thing is that in transformer as an impedance matching device, we have one formula that input impedance is equal to N1 N2 whole square into ZL. I am applying these two conditions to this figure. And what is Zin here? Zin N1, what is number of turns in the primary? N. What is number of turns in the secondary? 1 whole square into ZL. What is ZL? 5. Which is equal to n square into 5. Here, what is Rs is equal to 45 ohm. And equating these two values, n square, this is nothing but our RL, n square 5 is equal to 45, n is equal to 3. Okay. Next question number 7. Determine the current through 8-ohm resistor in the network shown below. Okay, let's see the figure in which we have to find the current through the resistor 8-ohm, which is nothing but I2. So we have to find the value of I2, and we know the input resistance Rn is nothing but N1 by N2 whole square into RL, which is nothing but N1 is what? 1 by 2 whole square into 8, which is equal to 2 ohm. And this information I am redrawing the figure as like this. Here the value of voltage source is nothing but 10 angle 0, 3 ohm, 2 ohm. Current I1 is equal to 10 angle 0 divided by 3 plus 2, which is equal to 2 angle 0 amperes. And we have the relation I2 by I1 is equal to N1 by N2, which is nothing but I2 by I1 is what? 2 angle 0, which is equal to N1 by N2, 1 by 2. Or we can say I2 is equal to 1 angle 0 amperes, right? Well, with this lecture, we are concluding magnetically coupled circuits. Before that, let me brief the topics we have covered in the magnetically coupled circuits. Introduction, in which I have covered self-inductance and mutual inductance, dot convention, equivalent inductance, in which series and parallel combination of inductance I have considered, energy stored in a coupled circuit and coefficient of coupling K, and an equivalent T and pi model of transformer for easiness of calculation. Okay, and at last I have solved some problems from magnetically coupled circuits, right? I am providing the link for all these topics in the description. Okay, so with this I am concluding magnetically coupled circuits. We will see again with another video. Till then, take care. Thank you.